All right, let's dive right into this. Welcome to today's Explainer, where we are tackling a foundational concept in statistics that, honestly, feels like a bit of a magic trick once you know how to use it. If you've ever stared down a massive dataset and just completely dreaded the thought of calculating every single measure of central tendency from scratch, well, you are exactly in the right place. Today, we're exploring the empirical relationship between the three main measures of central value. We're going to break down how they interact and, more importantly, how you can use just two of these values to instantly unlock the third. Here is the roadmap for today's Explainer. First, measures of central value. Second, the core empirical formula. Third, a step-by-step calculation. And finally, a real-world data application.
Okay, Section 1, Measures of Central Value, Establishing the Basics.
Before we get to the core mathematical formula, we need to firmly establish the variables we're actually working with, starting with the arithmetic mean. In our standard statistical notation, this is explicitly represented as x bar. Now, the mean is your classic average value, and depending on how complex your frequency array is, calculating an x bar can be quite an undertaking. You might use the direct method by dividing the sum of your observations by the total number of observations, or if you're dealing with larger grouped frequency distributions, you might have to use the shortcut method with an assumed mean, or maybe even the step deviation method using class intervals. Regardless of the method you choose, the end result is your x bar.
Next up, we've got the median, which is denoted simply by the letter m. If the mean is the mathematical average, the median is the literal middle of the pack. When you're looking at a frequency distribution, the median is the central value that splits your dataset perfectly in half. To find it, you're generally looking for the cumulative frequency corresponding to the n divided by 2 term, where n is the sum of your total frequencies. And once you locate that n over 2 term, boom, you've identified your median class.
Finally, we have the mode, marked with the notation z. Think of the mode as the most popular kid in school. It represents the most frequent observation in our dataset. To find it in grouped data, you first have to locate the modal class, which is simply the class possessing the absolute maximum frequency. From there, a specific formula involving the frequencies of the preceding and succeeding classes helps you pinpoint that z. Moving right along to Section 2, the core empirical formula, bridging the gap. Imagine a hypothetical data gap where you have the mean and you have the median, but you need the mode. Do you go all the way back and start from scratch? No way. Here is your bridge. Mode equals 3 times the median minus 2 times the mean. Just sit with that for a second. It is a stunningly simple core relationship connecting our 3 complex statistical definitions. It tells us that these central values aren't just isolated numbers floating in a vacuum. In moderately skewed distributions, they are predictably tethered to one another. So let's translate that plain English into actionable algebra using our standard statistical notation. Z slots into place for mode, M goes in for median, and X bar for mean. That gives us our star equation for today. Z equals 3M minus 2X bar. This equation is literally the heart of today's explainer. Which brings us to Section 3, step-by-step calculation, putting it into practice. Let's actually see how this works in a clear mathematical walkthrough. Imagine you have a dataset where you've already determined the median and the mean. Here are the steps to find the mode. Step 1. You take your calculated median, your m, and you simply multiply that value by 3. Hold on to that number. Step 2. You take your calculated mean, your x bar, and you multiply that value by 2. Step 3. You take the result from Step 2 and you subtract it from the result of Step 1. So you subtract 2x bar from 3m. Whatever number you're left with, that is your mode. That's your z. You've totally bypassed the maximum frequency formulas. It's vibrant, it's bold, and it's incredibly efficient.
And finally, Section 4, Real-World Data Application, the question bank.
Now, you might be wondering, okay, but when am I actually going to use this? Well, messy, real-world data is exactly where this formula shines. Take a look at this frequency array from the question bank. We have age brackets ranging from 20 to 60 years old and a massive number of persons surveyed. I mean, look at those frequencies. We're talking 50, 70, 100 peaking all the way at 180 persons in the 35 to 40 age bracket, and then trailing off. So the crucial point is this. If you were asked to find the mean, median, and mode of this specific data set, doing all 3 independently would take a serious chunk of time. You'd be setting up assumed means for the step deviation method just to get X bar. Then you'd be building a whole cumulative frequency column to find the n over 2 term for the median. But if you calculate just 2 of those,
let's say the mean and the median, this exact frequency array becomes the perfect candidate for applying our empirical formula. You just plug those two hard-earned numbers into z equals 3m minus 2x bar, and instantly you find the missing central value for this entire population. We've demystified the notations, we've walked through the algebraic steps, and we've seen exactly how much time this saves on large frequency distributions. Armed with the formula z equals 3m minus 2x bar, you can bypass hours of manual calculations. But it leaves us with a much bigger question. If these three measures are so predictably linked, what other hidden mathematical relationships are lurking in the messy data of our world, just waiting to be discovered? Thanks for joining me on this explainer, and happy calculating.